In the previous part of our Handmade interpreter, what we did is we made a lexer. So a lexer is something which takes a string input and turns it into a sequence of tokens. And now we have to turn this sequence of tokens into some object-oriented representation of the expression. Now, if you think about this expression, it's really a binary expression. So for example, 13 plus 4 is a binary operation. It has the left-hand side, which is 13. It has the right-hand side, which is 4. It has some operator in the middle, which is plus. And then we have a binary expression here in the minus, composed of two binary expressions on the left and right hand side. So you can see it's kind of a recursive definition, and we're going to define all the object-oriented structures for actually representing these kinds of expressions. We're going to begin by defining an interface. This interface is going to be called iElement, and the point of this interface is to define some operation which is common to all the types of expressions. So what is common to both addition as well as individual tokens? Because we're going to have individual tokens like 13 represented as literals, and we're also going to have binary expressions like 13 plus 4. And the common thing between a single literal as well as an expression is that they all evaluate to a numeric result. So we're going to have in the interface a property get called value. So here is a getter for a property called value, and everyone has to implement this. Now, we're only going to have two types of elements in our case. The first is an integer, like 14, for example. So we're going to make a class called integer, and this class is going to implement this iElement interface. Now, the whole thing about an integer is it just keeps a number, so we can get rid of this here. We can get rid of all this stuff, and we can just put a getter in here, and then we can initialize the value in the constructor as well, and that's it. That's all that an integer actually does. What's more interesting, of course, is a binary operation, because in this case we have to specify whether it's addition or multiplication, and we have to specify the left and right hand side. So I'm going to make a class here called binary operation, which is also going to be an iElement like so. And let's once again implement the interface, but this time around things are going to be a bit more exciting, because essentially what we have is, first of all, we have to define the type. So I'm going to make an enum here called type, and we have two types of binary operations. We have addition and subtraction, depending on whether we have the plus or minus. Now, of course, we have the type, public type, my type. Notice I cannot make it type, unfortunately. I cannot call it type. It has to be my type or the type or something like that. In addition, we have the left and right hand side of this binary operation. So public I element, and we have left and right. Okay, so I'm not going to make a constructor here. We're going to keep the default constructor, because remember, when you're at the very top level, when you're just interpreting the expression at the very top level, you don't know what the left and right hand sides are. You don't know what the type is, so we need a default constructor. I'm going to omit having any constructors so that I get an automatically generated default constructor for me. Now, the key thing here is how to calculate the value. How do we calculate this value? Now, we know what kind of expression it is. It's either addition or subtraction, and we know the left and right hand sides. And left and right hand sides are iElements, which means they have values of their own. So essentially we can do a switch here. We can do a switch on my type, like so. That's an enum, so we can alt enter and generate the missing labels. Now, in the case of addition, we return left.value plus right.value, and in the case of subtraction, well, you've guessed it, it's left.value minus right.value, and that's pretty much it. So we've now supported two types of nodes in our abstract syntax tree. We have the binary operation, which can be either addition or subtraction, and we have an integer which just keeps a number. Notice it's an integer, not a string. We're not keeping the string representation, although we could keep that as well in the abstract syntax tree if we wanted to, but we're going to ignore it in this case. So now the question is, well, given that we have a list of tokens, how do we turn it into a top level binary expression which contains sub-expressions and sub-expressions and so on and so forth? This is actually difficult to pronounce. Okay, so let's implement the parse method. That's going to be a bit more complicated than what we have in the lex method. So we're going to have a static method which returns an iElement, obviously, and it's going to be called parse. And what it does is it takes a set of tokens, so an I list of tokens, or maybe you want an I read-only list of tokens. So we're going to keep it read-only so that nobody tries to modify this list. So here's a list of tokens. And now we have to go through every single one, and depending on what kind of token it is, we perform a certain operation. So we have var result, and the result is obviously a binary operation in our case. If you look at this expression, you can see that there is a top level minus here, so that's a binary operation. So we're going to have new binary operation using that default constructor that was auto generated for us, and then we will also have a Boolean flag indicating whether the left hand side of this binary operation has already been initialized or not. So we'll have bool have left hand side equals false to begin with. Okay, so now I'm going to make a for loop where I go through each of the tokens. So from 0 to tokens.count, I have this counter I, and I'm going to get the token itself, var token equals tokens at I, like so, and then I will check the token type. So I will switch on the token.myType, and I'm going to once again alt enter and generate the switch labels. So here are the labels. The kind of tokens we can get are integer, plus, minus, left parentheses, and right parentheses. Although I'm going to get rid of right parentheses, you'll see why in a moment. So in the case when we have an integer, so we have an integer token, remember the integer token keeps the actual value as a string, we have to parse it. So we have to say var integer equals new integer. So that's our AST element, and here we have to parse. We have to say int.parse, and we take the token, and we take from the token the actual text. So we parse the text, we make a new integer, and then of course we need to decide where this integer goes. So if we don't have the left hand side of the expression, then we put it as the left hand side of the expression. So we say result.left is equal to integer, and then we have the left hand side rather. So now we have the left hand side. Otherwise, if we already have the left hand side, then we set the right hand side. So we say result.right equals integer. There we go. So this is how we interpret an integer coming in. Now for the plus and the minus, things are really easy, because all we have to do is we have to set the type of the result. So we say result.myType equals, and then we do addition here. So if it's a plus, it's obviously addition, and let's put a break in here. And similarly, in the case of a minus, it's subtraction. So let's get rid of this and add subtraction in here instead. Okay, so here's the challenging part. What happens when you hit an opening parentheses? Now what I'm going to do is I'm going to parse until I find the closing parentheses, and then I'll take the sub expression and parse it recursively. So I'll define a new variable called j with the initial value of I, and then I make a loop where there is no initialization, but then I go through all the values of j in the number of tokens. So I'll go through each of the tokens using the index j, so plus plus j here, and I say, well, is it a closing bracket? Is it the right parenthesis? If tokens at j dot my type is in fact equal to the right parentheses, then what I'm going to do is I'm going to break out of this loop like so, and now my j variable points to the end of the loop, so it points to the closing round bracket. And now what I can do is I can make a sub expression which is a parse of a sublist starting at the opening bracket and terminating at the closing bracket. So I can say var sub expression equals, and then I can get the tokens. I can skip the initial number of tokens up to the current one, and that has to include the opening bracket as well. So that would be I plus 1, because the token at I happens to be the opening bracket. And then of course I have to take the number of tokens at j minus I, and also minus 1, because I don't want the closing bracket either. So it's j minus I and minus 1, like so. Okay, so we have this I enumerable. I'm going to turn it into a list, and now we have a sub expression list. So once again, a list of tokens, and that list can be parsed. So we can say var element equals, and we parse that sub expression. We parse that sub expression, and then of course we perform the same operation that we did here. So we check whether we have the left hand side. I'm going to do it like this. So we check if we have the left hand side, and if we don't, then instead of assigning integer, we assign the element. Otherwise, we assign the element here, assign the element here, and I'm going to put a break, And of course, we already have the default, or rather, no, let's keep the default as is. So essentially, we're not handling right parentheses because in the left parentheses, we find the right parentheses anyway, and we handle it. We kind of skip it. And the way to skip it, by the way, should be down here below. So we set I equal to the value of j, thereby continuing this iteration of all the different tokens. And here towards the end, we return the result. So we return the result, and we can actually try and look at the structure of what it is that we are parsing. So I'm going to say var parsed equals parse the tokens, like so. I'll put a breakpoint here, so let's put F9 in here, and let's actually do a debug as opposed to just executing this. And we're going to take a look at what all the tokens have actually been parsed into, provided, of course, that I typed the program correctly, which I hope I did. Alright, so we are now in a breakpoint and we have passed our expression. So let's take a look at what we're getting. So the parse expression is a binary expression which has the left and right hand sides, and the type is subtraction, just like above you can see a minus. The left part is addition, which is of a left integer and a right integer. So the left integer has the value 13, the right integer has the value 4. So everything is correct. We have this nice layered structure of expressions. And what we can do now is we can actually evaluate this, because remember, we defined this interface. We defined an interface called iElement, which yields an integral value, and then the integer just yields its own value, whereas a binary expression performs the appropriate calculation. So we can now calculate the value of this expression after having interpreted this expression, and we can output it to the command line. So let's write line, and I'm going to say that the input is equal to parsed dot value. That's it. Now let's execute this, and here is the final result. 13 plus 4, 17. 12 plus 1 is 13. 17 minus 13 is in fact equal to 4. So that's it. We've used the interpreter design pattern and handcrafted both a lexer as well as a parser to interpret a numeric expression and evaluate its result.